Okay, this is the final video I'm going to make on steganography, and in this video I'm going to look at steganalysis. Steganography basically tries to hide the message, and steganalysis tries to uncover the message, and that's really as simplistic as it gets. So what are we going to look at? Well, first of all, I'm going to explain some of the basic techniques that we might use to look for a hidden message in an image. Simply, we're going to look for visual discrepancies, and this might be quite obvious. What we're going to do is we're going to compare the source image to the image that has been sent, and the image we suspect of having something hidden in it. We then compare them side by side, as you see at the bottom here, and we look to see if anything's different. It will be unusual for things to be different, as really, if it's been done right, there shouldn't be very obvious visual discrepancies. We can also check other things such as the size, the date modified, the date created, and all these things just to check if anything unusual pops up. A more advanced technique we might use is to look at residual artifacts, and this uses the SARC database. This database contains information such as the file name and the unique values that identify if steganography has been used. It also contains registry keys and values that are known to change upon installing a steganography application. If we see that these registry keys appear when we search for them, it will indicate the use of steganography, and that's quite easy to understand, I hope. And a good analogy here is that one of these registry keys could act like a fingerprint in a detective scene, because just one suggestion that there's been steganography at some time on this computer will basically confirm that they should keep looking. However, good cybercriminals will uninstall the applications, and that will cause the deletion of these keys. And this works using hash functions, which I'm not going to get into. But basically, hash functions simply change words into alphanumeric strings. Next, I'm going to talk about signature steganalysis. Your signature kind of acts like your distinct form of identification. It's what makes you you can make it unique to you. And some applications will leave these kind of distinct traces or these signatures when they're used. An example of this is JPEGs. What happens is when a message is inserted, some of the image aspects change. And in this example, when we use JPEGs as our method of inserting steganography or inserting the message, the end of the file's hex code is going to have this thing that you appear on the screen here, which says 5B3B315300. This is always going to appear when JPEGs is used. So when a message is inserted, this happens, and that's going to indicate strongly if it's been used, obviously. What a hex code is a hex code is a code that kind of represents the colour, and each of these 6-digit codes here is hexa for 6 and decimal 0 to 9. So we're going to use the first 6 letters of the alphabet, and we're going to use the numbers from 0 to 9 to represent everything. An example editor you might use is active at disk editor. The problem with this is if the image has been resampled or rescaled, then it's not going to work, as everything's going to be different. Next, I'm going to look at palette image steganography. Changing the least significant bit causes the color palette to be changed. So if we're using steganography and we're doing least significant bit like I looked at, it's going to change this color palette. And the palette is simply the range of colors. Steganography tries to limit these changes by using techniques to reduce the number of pixels that change color, which is what you'd expect, because we're really trying to make it less visible that changes have been made. By conducting statistical analysis of the palette table, we may be able to uncover if there's been changes. And this will generally look at the luminance element over the chrominance element. And this, as I've dealt with before, is because our eye is more perceptive of changes in chrominance. So people hiding messages generally hide them in the luminance, which we then look at. However, we'd probably look at both. Messages are then detected if we can see a large variation of colours in the palette. So we're really just looking to see if there's a big change in things, and that's the same for most of these techniques. We're really just doing the same thing in different fields. So in this one we're looking at the palette, in the previous one we looked for a signature, in the last one we looked for these specific keys, and that's true for quite a lot of the techniques that I've looked at. Next is noise floor consistency analysis, and in this one we're just looking for changes in the noise. Steganography attempts to hide these changes. However, there will almost always be a change in some of the noise in some of the components. So if a message has been inserted, and in particular we look at least significant bit, because this is the most common type of steganography as far as I can see, and we look at the noise profiles, and the noise profile is just the representation of the noise. If we look at this and we see anything unusual, it's highly likely that steganography has been used, because it's really common when we're looking for steganography for it to be least significant bit. And if we remember, noise is kind of just that kind of unwanted grain that you see in pictures or the static on TVs that's always there. Another technique is raw image steganalysis. And raw image steganalysis assumes that pixels are made up, or that images are made up of adjacent pixels. And what we're going to do is we're going to just do a lot of different calculations and comparisons, and then we're going to look at the values before and look at the values after and see if it looks different. And this was developed by Dimitrescu et al., I think is how you pronounce it, but I'm not too sure. So the pixels are classified into these 4 pairs, and we're going to complete this throughout the whole image. When a message is inserted into the least significant bit, the values are going to be modified. So obviously some of these are then going to be less than, some of these are then going to be greater than, and they're not going to stay the same. Since the 4 sets of values are changing, we can then conduct statistical analysis to indicate if a message has been placed. These techniques have all been quite simple to explain so far, as I just explained, as we're really, and even in this one, we're going to need access to the source image to look for differences, which is a disadvantage, as if you've not made the source image public, then it'll be much harder to use any of these techniques, if impossible. A more broad technique is just looking at statistical analysis, and this is known as statistical steganalysis. So what we're going to do is we're going to simply look at the statistics of an image. And obviously when a message is inserted, something's going to have to change. And that's always going to be true. It's always going to change something. I mean, no matter how well you do, something's changed to hide that message. By analysing these changed things, we can try and uncover the message, as you'd expect. So, when we use least significant bit steganography, the last digit is swapped to a 0 or a 1. And if you remember in binary, that's just the least significant bit. It just represents a change of plus or minus 1. The DCT coefficients will then be mapped onto one another, and this is if we're using JPEG, as they no longer exist, as it has either changed to a 0 or has been changed to a 1. So if you imagine what's happened here, we've actually moved the coefficients about since we've changed it to a plus 1 or a minus 1. No, to a plus 1 or a 0, I mean. And so instead of having them mapped in the same place, we're going to have a 1 where there was a 0 before. These zeros and ones are grouped into 2 and referred to as pairs of values. So these pair of values are the swapped kind of changes. We can then do a chi-square analysis on these pairs of values. And what chi-square does is it kind of tells you how likely a distribution is due to chance, due to change even. And then we can try and identify if a message has been hidden by the results of this analysis. And that's more complicated. One of the most advanced techniques I'm going to look at is this, which looks at the outguess algorithm. And it was developed by Friedrich et al. What this does is, the algorithm hides messages randomly in the least significant bit, as we've looked at, and it's going to hide them in the DCT coefficients, as we also looked at previously. So when the message is hidden, to counteract this change, other coefficients must be changed. And what this does is it ensures that if a histogram was conducted, the steganography would be less easily observed. And as you can see on the screen here, a histogram is just a representation of the distribution of data. When a message is inserted, there will be more noise in the DCT coefficients. This means there is more difference between 8x8 blocks of pixels. In turn, this means that there must be more changes made to ensure that between these 8x8 blocks there are less changes. And that's the process of what the steganography does. However, to conduct the steganalysis, what we're going to do, and it might seem unusual at first, is we're going to insert another message. So we presume that there's been a message hidden, and then we're going to insert another one onto the same picture. We do this as adding another image will generally cause less increase in discontinuities than expected if an image has already been embedded. Basically what that means is there's going to be less change if it's previously had steganography hidden in it if we hide another image in it. The size of the increase is what is used to gauge the size or the presence of the hidden message. Message is detected by comparing the histogram with the unaltered histogram. So that's how we're going to do it. We're going to compare the two histograms. And this can be used to find the number of changes to an image, which helps indicate the actual message and what it might say, as opposed to the other techniques I've looked at, which kind of just indicate if there has been something used. Another technique was developed by Avkebas et al. This uses image quality metrics, or IQMs. Some examples of IQMs are the sharpness, the noise, or the contrast of an image. What this algorithm does is it differentiates the cover image from the image with hidden messages. It conducts a statistical test and will rank the IQMs of an image based on their score. This identifies the message. It is identified as some IQMs are sensitive to message insertion, so can easily be measured. So if we insert an image, and I'm not saying this is true, this is just an example, maybe the sharpness is going to be vastly different to the previous message, or the contrast. And these changes, as I've looked at, are what we're going to use to indicate the presence of a secret message. By looking at several of these at once, we're going to have a much higher success rate, as we can conduct more analysis and can compare more fields to see for changes. And finally, we've got neural networks, and I've written this on the screen. And neural networks are a developing way of using steganography or steganalysis, and they are a bit more complex to understand, so I've included it here. A neural network kind of tries to reassemble a brain. It's kind of artificial intelligence-y. And a neural network is set up to try and detect the steganographic information encoded in images. What it's trying to do is it's trying to make it automated. You're trying to teach this network to be able to detect images for itself. So it's quite similar to traditional techniques in a way, but what happens is it's set up to look for a specific type of data. So it'll also look at a set of data, such as the DCT coefficients in JPEG, which is a common one, because that's commonly where things are hidden. What then happens is we feed this network and we make the network look at a series of images. So we're going to run them through the network and we're going to try and help them identify if it's got steganography or if they don't. By feeding the message these images, we're going to attempt to be training them in a way. So we're going to be trying to make the network understand what is steganography and what isn't. And one paper I read found that it had a 70 to 80% detection rate, which is quite high, if you imagine it. However, 20 to 30% of the images were therefore not detected, so there'll be a lot of false positives as well. So this is basically the field that has the most promise for automation and for making it sure that messages will always be detected as a computer's doing it, so there's less chance of error. And that's all the techniques I'm going to look at for now. Thank you for listening.